Hello everyone. Today's lecture will be about chemical calculations part 2. So in the previous chemical calculation part 1, we basically dealt with basic mole calculations. Today's one will be dealing with titration calculations and empirical formula calculations. So let's start. So titration, what is titration? It refers to the process of determining the endpoint of reactions involving acids and alkalis or bases. So you can either have acid-alkali reactions or you can have acids and base reactions, right? So it makes use of an indicator, for example, phenolphthalein methyl orange, to pinpoint exactly when a reaction has reached completion. By knowing when the reaction ends, we get to determine the exact volume of a substance which needs to be added to neutralize another substance. So of course, acids and alkalis, the reactions between acids and alkalis, they're called neutralization reactions because one of the substance neutralizes the other. And when the neutralization does happen, we have to be able to understand when the neutralization actually happens by the use of an indicator. The indicator will point us towards the point where it's actually neutralizing one or the other. So to carry out this process, we have to follow a few steps. So these are the steps of carrying out titration. The first thing that you have to do is you have to pour 25 centimeter cube of aqueous sulfuric acid of a known concentration. Of course, you have to have the concentration known from before into a conical flask using a pipette, and then add a few drops of methyl orange to it. The color will turn red. So of course, the methyl orange, it has reddish color in acids, and in neutral it is orange, and it is in alkaline solutions it is yellow. So in here, because we are pouring the methyl orange, a few drops of methyl orange into the H2SO4 acid, it's going to turn red. So you have to transfer the H2SO4 acid using a pipette, because a pipette is used to transfer a specific volume of any aqueous solution or liquid, right? So you have to transfer exactly 25 centimeter cube of H2SO4 acid using a pipette into a conical flask. And then what you have to do, you have to use a burette to slowly add aqueous sodium hydroxide solution of unknown concentration. You do not know the concentration of this one. This is what you have to find using titration calculations until the color of the mixture in the conical flask turns orange. So like I said, at the end point of the titration reaction between an acid and an alkali, when the end point is reached, the methyl orange will turn orange, and that is what happens. So you have to keep on slowly adding the sodium hydroxide solution from the burette until all of it is neutralized. The sodium hydroxide and the sulfuric acid, they neutralize each other. Until that happens, you have to keep on adding. So how will you know when that happens? When the solution turns orange. That is when you will understand that yes, the titration has been completed and the neutralization has occurred. That will indicate that the reaction has reached end point because the alkali has been able to fully neutralize the acid. So step number 3 is, while adding the alkali, keep swirling the conical flask for even mixing. So of course you are adding the alkali from the burette, but while you are adding the alkali, you have to make sure that the conical flask, it's being constantly swirled by the other hand. You have to use two hands, of course, one hand to slowly add the alkali from the burette, and the other hand to continuously swirl the conical flask which contains the acid, so that there is even mixing. You have to make sure that the mixing is even. The alkali and the acid, they mix evenly. So this is what the setup looks like. As you can see, this top thing, this is the burette, this thing, and this is the conical flask, right? This is the tap using which you have to slowly add the alkali from the burette. And of course the color change will happen like this. In this situation, it is they're using phenolphthalein in this case. You have to use, of course, some other indicator, which is methyl orange, right? So now sample calculation. So sample calculation, this one is a reaction taking place between sodium hydroxide and sulfuric acid to form sodium sulfate and water. So this is a proper neutralization reaction. And in here, as you can see, 2 moles of sodium hydroxide end up reacting with 1 mole of sulfuric acid to form 1 mole of sodium sulfate and 2 moles of water. So using this equation, we have to actually solve this example. 25 centimeter cubes of a 0.05 mole per dm cube H2SO4 sample was neutralized by 50 centimeter cube of the NaOH. Find the concentration of the NaOH. So you are provided with the volume as well as the concentration of the sulfuric acid, and you're also provided with the volume of the alkali. So you simply have to find the concentration of the alkali. So moles of sulfuric acid, as you can see here, to find the number of moles of the sulfuric acid, you have to multiply the concentration with the volume. That's what I did. 0.05 is the concentration, and the volume in dm cube is 25 by 1000. This is what we got. And the moles of NaOH would be what? Using the mole ratio, it would be twice of it, as you can see, because 2 moles of sodium hydroxide reacts with 1 mole of sulfuric acid. So whatever the moles of sulfuric acid you got, you have to multiply that with 2 to get the moles of NaOH. That's what I did. So I got the moles of sodium hydroxide to be 2.5 into 10 to the power minus 3. Now that I know the number of moles of sodium hydroxide and I also know the volume of the sodium hydroxide, the formula for concentration is number of moles divided by volume. So this is the number of moles. Divide this with the volume in dm cube. I got the concentration in moles per dm cube. Okay, this is how you actually carry out a titration calculation. Then the next part is regarding empirical formula. It is the shortest possible formula of a substance. So to find the empirical formula, you have to follow the following steps. You have to divide the percentage abundance of the constituent elements by the respective molar masses. Then once you've done that, you have to divide the answers that you obtain in step 1 by the smallest. So whatever the smallest value we get, you have to divide all the answers that you got in number 1 by the smallest value. And then once you've done that, the answer that you get, rearrange the answers obtained in step 2 with the respective elements. So let's show a calculation. So in here, sample contains 12 grams of carbon combined with 2 grams of hydrogen. Find its empirical formula. The first thing that you have to do, you have to divide the percentage abundance of the constituent elements by their respective molar masses, right? So you have to first find the percentage abundance. So percentage abundance of let's say carbon. So out of the entire thing, how much mass does it have? It has 12 of carbon and 2 of hydrogen. So it has a total mass of 14, right? Out of the 14, 12 is carbon. So if I find the percentage abundance of it, this is what I get. And to find the percentage abundance of hydrogen, I carry out the same thing. Out of 14, we can see that hydrogen only, consists 2 gram of the 14. So now if we put them in the calculator, 12 by 14 times 100%, we get 85.7%. And for the hydrogen, it would be 14.3%. Okay. So now that we know the percentage abundances, the steps, let's go for the steps. So we have carbon here, we have hydrogen here. So first step is divide the percentage abundances by the molar masses. So percentage abundance of carbon is 85.7 divided by its molar mass is 12. That's what we got from the periodic table. For hydrogen, it is 14.3 and the molar mass of hydrogen is 1. So what do we get? The answer over here is 85.7 divided by 12, which comes to 7.14. And for this one, it comes to 14.3, right? So now, which is the smallest out of these two? Of course, 7.14. So you divide both of them by 7.14. So second step would be 7.14 divided by 7.14 is to again 14.3. This is also getting divided by the smallest because you have to make sure you divide both of them at the smallest. So what do we get? We get here 1 and we get here 2. 14.3 divided by this, we get exactly 2. Okay. So what do we do in the third step? The third step, I said you have to rearrange the elements along with the numbers that you got here. So what can we see here? That carbon and hydrogen, they are reacting in the ratio of 1:2, meaning what? That 1 carbon is combining with 2 hydrogen atoms. So this is the empirical formula of this substance that we were provided with. So that means in this substance, every carbon atom would be bonded with 2 hydrogen atoms. Okay, so like I said, this is the shortest possible formula for substance. As we know, CH2, there is nothing called CH2, right? CH2, because carbon has 4 electrons in its outer shell, it has to bond with 4 other entities. It's just bonding with 2 other entities over here, 2 hydrogens. So of course it's not a complete thing. So this is just the empirical formula. It's the shortest possible formula of this substance. So let's say we want to get the actual formula of the substance. So what do? We have to find the molecular formula. So let's go on to the molecular formula. So to find the molecular mass of the sample in the previous page was 56 grams. So the thing that we found on the previous page, this is what? CH2. This is the empirical formula of the substance. So if I want to find the molecular mass of the molecular formula of the substance, I have to make use of the molecular mass of the substance. So the molecular mass of the substance that we used in the last page, it is actually 56 grams. So how do I find the molecular formula from the empirical formula? This is actually the way to do it. The molecular formula mass is N times empirical formula mass. So what is the molecular formula mass for this one? 56 grams. Okay, this is the actual mass of the molecule, right? We are wanting to find We're wanting to find the actual molecular formula. So if I want to find the actual molecular formula of the substance, which is having a shortest possible formula of CH2, like I said, CH2 is not a real substance. It's the shortest possible formula of the actual substance. So this is the shortest possible formula of the substance, called the empirical formula. And if I want to find the actual molecular formula of the substance, I have to make use of the molecular mass of the substance, which is 56 grams. So using the actual molecular mass of the actual substance, and with the empirical formula mass, I will find the actual molecular formula of the substance which we analyzed in this example, where 12 grams of carbon combined with 2 grams of hydrogen. Okay, so we will find this actual molecular mass and molecular formula. So 56 grams is the molecular mass of the substance, and N is something that I have to find, and the empirical formula mass. Empirical formula mass means the mass of the empirical formula. So the empirical formula that we found was CH2. CH2, right? So what is the mass of CH2? We have 1 carbon, which is 12, and we have 2 hydrogens, which is 2 into 1. So what do we get over here? These many grams, of course, because that's the mass. So 56 grams is equal to N times, that is what, 12 plus 2, which is 14. So 14 grams. So what do we get? N is 56 grams by 14 grams. So you cut them off, you get exactly 4. So N is 4. What does that mean? You know what that means? It means that the molecular formula is equal to, it is N times the empirical formula, right? That is what we wrote here. Whatever the molecular formula is, it will be M times the empirical formula. So here the molecular formula would be what? Molecular formula would be 4 times, because the N, the value of N we found to be 4, it would be 4 times the empirical formula, which was how much? CH2. So we write it here, CH2. So what do we get? 4 times CH2 means what? There are 4 multiplied with C, that means 4 carbon atoms, and 4 multiplied by H2, meaning what? 8 carbon atoms. This is the actual formula of the substance which we analyzed in this example. This example we found, using the data given, we found its empirical formula, but to find its actual formula, we had to do another step. Using the molecular formula mass in the empirical formula mass, we found the multiplier, which is N. And once we found the multiplier, we multiplied this multiplier with the empirical formula that gave us the actual molecular formula. So like I said, empirical formula is the shortest possible substance, shortest possible formula for substance. And if you multiply this with a specific multiplier, which is suited only to that question, okay, because this is for only for this question. For other questions, it will be different, of course. So of course, for this question, it is 4. So that means what? That for this question, whatever the empirical formula that I found, the shortest possible formula that I found, I have to multiply this with the multiplier, which is 4, to get the actual molecular formula of the substance that I analyzed in this example. Okay, so the actual formula comes to C4H8, which is, this is actually butene. And butene, as we will learn later, is an organic substance which is part of the alkene family. Alkene. And alkene family, in the alkene family, every member has the empirical formula of CH2. Why? Because in the alkene family, whatever the number of carbon is, every member having carbon number, whatever they will have exactly twice the number of hydrogen as far as carbon is. As for the number of carbon atoms that they have, the hydrogen would be exactly twice. So C4H8, then we'll have C5H10, we'll have C6H12, C7H14, and so on and so forth. So whatever the carbon number is, all of the alkenes will have exactly twice as much hydrogen as carbon. Now this one, this is a question which has provided some information. So gypsum is basically hydrated calcium sulfate. Okay, we have to find the N, the number of molecules of water of crystallization, which is not here. We have to find it. So what are the what information are we provided with? We are provided with the mass of the crucible, the container, empty container. Okay, and this is the mass of the crucible plus the gypsum. Gypsum is actually the hydrated calcium sulfate. So to find the mass of just the gypsum, what do? I subtract from 45.94, I subtract 37.34. So I got 8.60 grams. Then the next piece of information is mass of crucible plus the anhydrous calcium sulfate. Anhydrous means what? That the water has been evaporated. So after the water has been evaporated, we are just left with the calcium sulfate. The water is gone, right? So this is the anhydrous calcium sulfate without the water. So if I want to find simply the anhydrous calcium sulfate's mass, what do? I subtract from 44.14, I subtract 37.4, because this will cut off the mass of the crucible. Just like in this one, we cut off the mass of the crucible. In here as well, we have to cut off the mass of the crucible to get just the value of the anhydrous calcium sulfate, which came to 6.80 grams. Now, the last part that's left is you have to find how much water has been evaporated, how much water was actually present. So if you look over here, the hydrated sample's mass was 8.60 grams. This one was the gypsum's mass, which contained the water, and this one is the anhydrous calcium sulfate's mass, which does not contain the water. It means what? This means that the difference between them will give us the mass of the water which we evaporated. So that's what I did. I subtracted this and this to get the mass of the water, which is exactly 1.80 grams. Okay, 1.80 grams. So you can either subtract this minus this, or you can subtract 8.60 minus 6.80. They will both give you the same answer. Here as well you'll get 1.80, right? So it doesn't matter which one you take. You can take either subtract this minus this, or you can subtract this minus this. Both are absolutely fine. Now that we know the mass of the calcium sulfate and we know the mass of the water, okay, we know the mass of calcium sulfate anhydrous, and we also know the mass of the water, okay, and together these two masses combine to form the gypsum. So if you add these two, 6.80 plus 1.80, you're going to get 8.60. That is the total mass which contain both the water and the anhydrous calcium sulfate. So now we want to find the value of N. To do so, we have to again take the help of the empirical formula. So again we write it, calcium sulfate anhydrous, right, and then you have water. So first step is, of course, you have to find the percentage abundance. So let's find the percentage abundance first. So percentage abundance of calcium sulfate would be how much? Let's do it here on the rough. So out of the entire mass, which is 8.60, out of this 6.80 is the anhydrous calcium sulfate. So it's 6.80 divided by 8.60 into 100%. This should give us the percentage abundance of calcium sulfate. And for water, we had 1.80 grams of water out of 8.60 grams of the entire thing. So 1.80 divided by 8.60 into 100%. That's going to give us the percentage abundance of water. So 6.8 divided by 8.6 times 100%, which gives us 79.1%. So 79.1% is the percentage abundance of calcium sulfate. And for water, it's going to be 20.9. 20.9. This is the percentage abundance of water. So now what do? We divide them by the molar masses, right? We divide them by the molar masses. So the molar mass of calcium sulfate would be what? Calcium is 40, sulfur is 32, oxygen, there are 4 of them, so it should be 16 times 4. For water, there are 2 atoms of hydrogen, so each atom of hydrogen has mass of 1, so 1 into 2 plus oxygen is 16. So what are the answers? This one is 79.1 divided by those things, 40 plus 32 plus 64. We get 0.582, and this one we get how much? 20.9 divided by those things, which is 16 plus 2, 18. It comes to exactly 1.16. okay, now what is the next step? Second step is to divide both of them by the smallest. So the smallest here is 0.582, so we divide both of them by the smallest. What do we get? This is 1 and this is 0.582. You divide this by 0.582, we get exactly 2. So what does that mean? That means that the calcium sulfate and the water, they are combined in the ratio of 1:2. That means for every calcium sulfate, every mole of calcium sulfate, we have 2 moles of H2O. So what can we say? That every mole of calcium sulfate is in combination with 2 moles of water, right? 1:2. So 1:2. So 1 mole of calcium sulfate with 2 moles of water. So what does that give us? It gives us the value of N, because in the last, as you saw over here, N is what? How many moles of water we have. So as you can see, here we have what? CaSO4 means what? 1 CaSO4. So 1 calcium sulfate with how many? With N moles of water. So 1 mole of calcium sulfate with N moles of water. This N we found to be 2. How? Because we had to find how many moles of water reacted with combined with 1 mole of calcium sulfate. So 1 mole, we found that each mole of calcium sulfate is in combination with 2 moles of water. So that's why the value of N should be 2. So N should be equal to 2. This is how you find the value of number of molecules of water crystallization. Then finding which reagent is in excess. So example is 25 centimeter cubes of this sample of sodium carbonate is reacted with 20 centimeter cube of this sample of HNO3. Find out which reagent is in excess. So this is the chemical equation. So using these values, 25 centimeter cube and 0.3 moles per dm cube, we found the moles of Na2CO3, which came to this much. And using these information, 20 centimeter cube and 0.4 moles per dm cube, we found the moles of HNO3, which these are the actually the proportions in which they have been reacted in this reaction. Okay, so if we actually want to find which one is in excess, which one is not in excess, we have to first refer to the mole ratio. So if you look at the mole ratio, each mole of sodium carbonate is reacting with 2 moles of HNO3. So it's 1:2. 1 mole of sodium carbonate reacts with 2 moles of HNO3. So here we know the moles of Na2CO3 present, we know the moles of HNO3 present, but what is the required moles of HNO3? So sodium carbonate, whatever the moles are, the HNO3 would be twice as much. So if the Na2CO3 mole that we used here is 7.5 times 10 to the power minus 3, the required mole of HNO3 should be how much? 2 times of it, because the mole ratio is 1:2. So if you multiply this with 2, what are you going to get? You are going to get 0.015 moles. So this is the mole, this is the amount of mole that you need for the reaction to be exactly in sync, right? You need for 7.5 times 10 to the power minus 3 moles of Na2CO3, you need exactly 0.015 moles of HNO3. But as we can see here, our reaction actually made use of 8 times 10 to the power minus 3, meaning what? Meaning that even though I required 0.015 moles of HNO3, I only got this to react with 8 into 10 to the power minus 3, meaning what? Since we have lesser number of moles of HNO3 available than is needed, so we need 0.015, but we have only 8 times 10 to the power minus 3 available. So because we have lesser number of moles than we need, it means HNO3 is deficient. So this one is, of course, it was used lesser than it should have been. So if this is deficient, we can say what? In other words, we can say that conversely, this means that Na2CO3 was used in excess. So because, like I said, for Na2CO3, for this much of Na2CO3 to be completely reacted, we need exactly 0.015 moles. But we didn't have 0.015 moles, because how much did we have actually? 8 times 10 to the power minus 3. So even though we required 0.015, we only had available 8 times 10 to the power minus 3, meaning what? That this one was deficient, that HNO3 was deficient, meaning what? If HNO3 was deficient, we can say in other words just the opposite thing, that sodium carbonate was actually more than what it should have been. Okay, last thing is finding percentage yield. So it refers to how much of the theoretical yield of a reaction we end up getting experimentally. So we expect something and we get something else. So percentage yield is the experimental value of any substance that you found in the reaction experimentally, and theoretical value is what you expected by theory. Then you multiply this with 100%. A reaction resulted in the formation of 5.6 grams of NaCl. This is what we got experimentally in real life, while the expected mass was 7 grams. You expected to get 7 grams of NaCl, but you only got 5.6 grams. So you put this in the formula. Experimental value is 5.6, and the theoretical value was 7. We get 80%. So whatever we were expecting of the NaCl mass, we only got 80% of that, because you will never get 100% yield, right? So this is the end of basically the mole discussion. Chemical calculation part 1 discussed with basics of moles, and chemical calculation part 2 dealt with the remainder. So thanks for watching the video, and thanks for listening to the lecture.